Okay, Zach says we're ready to go. So just a couple things before I introduce our speaker tonight, Steve Grimes. First of all, welcome to those who are watching us on YouTube. No longer Zoom, we're doing YouTube now. And those of you who are here, thank you for coming out in this weather. A couple things real quick. Number one, on the table over there, we've got some free fossils with a description of what they are. So especially you young ones, go get one. Secondly, if you're not someone who attends Bethel and you'd like to take some information back to your pastor, we have something on the table over there. We just came out with this tract, and I'm going to give everybody one, and we're selling them 25 for $5. So if you're interested, you can do one of two things. You can buy some tonight, or on the back, there's a QR code that you can hit, and you can buy online, and we'll send them to you. Also on the back, this tract, it's called Systems, and it is very specific about the complexity of the systems of the human body. We pull out the circulatory system and talk about it. But there's on the back also, there's a QR code that will take you to this video that we did. We called it One Day Over Coffee, starring Scott Jarris back there.
Thank you. I was co-star.
Yeah. It was Scott and I that did this. And there's some sheets on the table there that will tell you how to get there. But it's, the premise of it is that I'm sitting in a coffee shop and Scott, I've got my computer open and Scott walks in. I haven't seen Scott since college. We strike up a conversation that of course leads to talking about origins. And it is, hopefully it's interesting to you. You'll learn a lot, honestly. You'll learn a lot. It'll give you some talking points when talking to skeptics, etc. So these are on the table over there, but there's a QR code that goes specifically to a certain point in this video that it'll take you there. Come on in, folks. So tonight our speaker is Mr. Steve Grimes, and Steve has been keeping up with first of all, Steve, you've been one of our speakers for how long now?
Oh boy.
Well, you were a speaker when we were here, I always say BC. We did a series of classes here in 2019, BC being before COVID. I think that's how to separate it out now, but
yeah.
You were a couple of years before that, right?
Yeah, at least that's that. I've been here before, so.
Yeah. So Steve's been one of our speakers for a long time, and Steve has been keeping up with the James Webb Space Telescope. And he did a presentation for us a year ago.
1 year ago, yeah.
1 year ago this month. And we decided to have him because they're finding out things that they've never expected to see.
Yeah.
And Steve's been keeping up with that. So he's put a presentation together for you. So please welcome Steve Grimes.
Thank you, Mark. Thank you, Zach, for all the technical things you do that make it seem so easy to the people out there in the interwebs. So, a great crowd for the weather and all. I appreciate you're giving it a try. And yes, tonight's talk, the heavens still declare the glory of God. What the James Webb Space Telescope is revealing about creation. All I had to add from last year's talk was the word still. So it wasn't as much work this year as it was last year to put this together. But I did put in some new things. So you'll hopefully get to see that. This is my background. That's also on our website. It's not that special, actually. So we'll keep moving on. What we do have is, I did put up an agenda, and this is what we'll cover tonight. And forgive me if I forget to turn with the mic and up the mic. I do that, sorry. Oops, need to go like this, right? And you can all hear me okay if I do it this way? Yeah. Can you not hear me if I do it this way? Not really. Okay, I'll try to keep the mic where it should be. Anyway, yeah, this is roughly our agenda. It's roughly the same agenda as last time, but I do have some new things that have come in this past year. Bottom line, it's going to take many years to digest all of the data that is being pulled in, many, many years. And so some of the articles that are out there even now saying, give us another year, give us another year. We need to keep processing this and figuring things out because at this point, there are more questions than answers. Interesting findings, but we'll see that as we go through this. First of all, God's word about the heavens. Anyone know which galaxy this is? Anyone recognize it? It's our closest neighboring galaxy. That's a hint. Andromeda. This is the Andromeda galaxy. I think it's way, way bigger than the Milky Way galaxy that we're in, but it has roughly the same mass. Space is full of questions. One of the last questions we'll get to, I don't know if you noticed this on the agenda, how can your creation be young when starlight is old? Because that's a question we always get. Well, we touched on that with a whole presentation about 2 years ago, but as soon as we leave this planet, we get more questions than answers. For instance, why is Andromeda so much larger than the Milky Way, but roughly the same mass? That's something we won't address tonight. But let's look at what God's word says about the heavens. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day, they pour forth speech. Night after night, they reveal knowledge. They have no speech. They use no words. No sound is heard from them, yet their voice goes out into all the earth. Their words to the ends of the world. Very famous passage from the Psalms. And so when did these stars come about? Well, God tells us in his word, he created the stars on, anyone know the day? Fourth day. And God made 2 great lights, the greater light to rule this day and the lesser light to rule the night. And he and just almost as an afterthought, and he made the stars also. It is in some versions. I picked which version I like, and I'm using ESV for these. Another passage from 1 Corinthians mentions stars. They're actually mentioned a fair amount. One of the points I like to make is we don't have a word for comets, meteors, planets, planetoids, meteorites. We don't have words for those things. And so I think stars covers many of these other celestial bodies that we would see. And there is one glory of the sun, another glory of the moon, and another glory of the stars, where star differs from star in glory. And of course, we know that even more today than ever before. Lift up your eyes on high and see who created these, who brings out their host by number, calling them all by name, by the greatness of his might. And because he is strong in power, not one is missing. My point in bringing these out is that the Bible is not silent on the heavens. It makes a very strong point about the heavens. If you wonder about God's power, look into the heavens. So what we are about to see is amazing. Remember, God says you need to see that. You need to look at that because, yes, I'm the creator of those things. He determines the number of the stars. He gives to all of them their names. Well, this is a particular constellation of stars. Anyone recognize it? This would be like you'd get extra points if you recognize this. This is the Pleiades. Pleiades, also known as the Seven Sisters. And what's remarkable about this testifies to, again, God's truth, that there was a common set of knowledge shared by all mankind before man was distributed across the planet. So what do we have today? We have Aboriginal cultures, we have the Greeks, we have cultures in South America, all with similar stories about the Seven Sisters, which are pointing to this constellation of the Pleiades. It's called the Messier 45. And it's known by 7 sisters or 7 brides or 7 wives. I mean, when I look at those, I don't really see the female form anywhere in those bright spots, but apparently across the world, this is known in similar terms, similar to the flood legends, the flood stories that have gone on across the world, and they share similar features of the global flood. How would that be known by people in South American and North American, Native Americans, as well as, again, Aboriginal Australians and so forth? I think it testifies again to the truth of God's word and God's story of how this all came together, as opposed to some long ages evolutionary tale. But I just threw that up there as an aside. First, we'll look at the Hubble Space Telescope, because really we've had 30 years now of Hubble, and it has been marvelous. The Hubble Space Telescope was a breakthrough. It's orbiting around the Earth. And we've had to repair it, pretty big repairs once, maybe more than once, but at least once that I know of. And it's given us remarkable images. and it's allowed us to peer way, 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 way deep into space. Now, there is an attempt to equate light years, which is a measure of distance, with time, because, well, a year is time, right? When you get into space, that's not necessarily an equation, an association you can make. We'll get into that later too. The physics on this stuff is pretty crazy. But anyway, the Hubble Space Telescope, giving us these wonderful things, the giant red nebula, NGC. This is, you may have seen the Messier 41 or 45, actually, a number I saw earlier. There's really two big catalogs out there. There was this French guy named Messier back in around 1770, 1780. And he just looked at everything he could see. He loved comets. He loved comets so much, he wanted to rule out everything that wasn't a comet. And so he started writing down all the things he could see that weren't comets. Well, it's now known as the Messier catalog. It includes Andromeda, it includes the Pleiades, includes all these different things. And there's also a new classification system. The N in NGC stands for new. It has to do with classification of stars, of nebula, and so forth. One of the more famous pictures from the Hubble was the so-called pillars of creation. What's remarkable about this, one of Hubble's most iconic images, is the portion of the Eagle Nebula, M16, dubbed the Pillars of Creation. It shows three huge columns of cold gas illuminated by light from a cluster of young stars. The largest of the three columns is approximately 4 light years tall. That's a lot of space. That is way larger than even our whole entire solar system. Okay, so what is a light year? I thought I would put up this particular. I know it'll play for me if I do it from over here. So let me just walk over here. It's going to take us all the way down to our sun. There's 1 light year. Gets us up to 100 light years. Now we're back to the Milky Way. So that came from NASA. You may have seen it mentioned, the Oort cloud, 29 light days or something else. I don't hold to the Oort cloud. It could be there, but they've admitted there's no way to tell if it's there. There's been no observation of it being there. The only reason it exists is to explain comets that are far younger than our solar system is presumed to be. And so to explain away young comets, they created the Oort cloud, which occasionally pops a comet into our solar system so that we can see it and know that it's going to be gone in a few thousand years. How could that be? Can't be 4.5 billion years old then. So anyway, there's also the next thing. If there's time at the end of this, I'd like to do the what's coming next after James Webb. They've already figured out what to do next in terms of this telescope. And it's pretty remarkable. But we'll see if we get time for that. Oops. Nope. Let's move on. So the Hubble image, the Orion Nebula, just another one of these, the billion pixel composite. This downloads sometimes take hours from these telescopes, and then they assemble it all together and they get these remarkable pictures. What you see is as colors here, they're actually taking the metallicity of the cloud, they're taking the different element compositions within the cloud and using that they're mapping to colors with that. So those colors aren't real. They're mapped based on a fixed table. They're saying, okay, we're going to show iron this way, or we're going to show excess carbon and more oxygen. We're going to mix these different elements and show them as different colors, just so that you can see that we see variety in the metallicity of these clouds and of the stars and so forth. And it's a really key thing. There's only so many things you get from a star. You get its luminosity, you get the spectrum, the metallicity, which is what kind of metals it's made up of. You don't get much more from observing a star. We are pretty limited in terms of science. We can't put these stars in a laboratory. We can't conduct experiments on the cosmos and rerun those experiments. So there's going to be a whole lot of conjecture about everything we see, and that's fine. I get that. What I don't get is that there's very little humility. They just state things as though they're absolute fact. I've not seen stronger dogma. Well, maybe in the evolutionary biology community, but you just get this dogma. This happened. This happened. This happened, and then a week later, somebody publishes another paper. Well, none of that happened. You'll see an example later in a minute. The other thing you'll see is repeating often. Discoveries highlight finding planetary construction zones. Almost everything you read about James Webb and about Hubble and about NASA's mission here is to find how life originated, how everything originated. They are pushing the whole origins narrative with all of their programs and missions and packages. And really, when you get right down to it, we see these nebular clouds that are full of these different metals and things, and that's what we see. Now, we can wrap a story around that and say, well, that's a cloud, that's a planetary forming area of the system, or we can say that's a star formation area. But really, there are problems in physics with all of the theories about star formation and planet formation that we don't have time to get into today, but we might touch on a couple. So I'm just mentioning here that you will see on almost all the pictures, and if you look at any of these things on the web, they're all couched in the terms of how things came to be and how they have no idea. The real problem is they have no idea, and they won't admit it. They want everyone to know that there's no way God was involved. Well, I rely more on a scientist like Isaac Newton, who totally said God's involved. You know, we live in a remarkable time, not only of this marvelous technology that lets us see these amazing things in space, but now on the internet, the archives include a lot of the ancient documents. You can pull up Newton, you can pull up the church fathers, you can pull up ancient manuscripts in Greek and in Latin. It's really remarkable. Anyway, this is one of Newton's greater works, and in it, I won't make you read the fine print. This most beautiful system of the sun, planets, and comets can only proceed from the counsel and dominion of an intelligent and powerful being. And if the fixed stars are the centers of other like systems, which we now find that they are, we'll talk about exoplanets in a little bit. Yeah, we find planets. These are other systems built around other stars. Well, Newton said, yeah, that's going to probably be found as well. These, being formed by the likewise counsel, must all be subject to the dominion of one. So he gives credit to the Creator because he realized the precision of the arrangement of what's going on, especially in our own solar system, that they could see the best, defies any naturalistic, plausible, materialistic explanation. Okay, so last bit about God's Word, this section of our talk. For the mind, why is it that man is so bent on explaining this apart from God? And it's not just because we're in pursuit of science, because I'd say Isaac Newton and Johannes Kepler, these guys were in pursuit of science. It's the misdefinition of science, and it points to the depravity of man. For the mind that is set on the flesh is hostile to God, for it does not submit to God's law. Indeed, it cannot, as it says in Romans. And this is the verdict. Light has come into the world, but people loved darkness instead of light because their deeds were evil. Okay, so one last Hubble image. This is from the Crab Nebula. This was a neat one. This was actually observed in China around 1054 AD. They saw this huge explosion in space, and we can still see the remnants of it today and all the different chemicals that came from this. This speaks to the life cycle of stars. And so one of the things I want to clarify too is I don't deny that stars have a life cycle, that we don't see stars exploding today, or that we don't see formations that seem to be heading toward perhaps the construction of another star. It actually takes an exploding star nearby to push things together. Everything has to line up just a certain way to overcome the forces of physics, which would prevent star formation. But I'm not saying it's impossible that a star could form naturally. I'm just saying these are inadequate explanations to explain what we're going to see. Okay, let's look at that life cycle of stars. This is stellar evolution. This is from the Encyclopedia Britannica, and you'll see that there's a nebula, and that's basically your cloud. And then from this cloud of metallicous gases, by the way, in a second, I'll talk about population 3, population 2, and population 1 stars. And for some reason, the astrophysicists have numbered them backwards. 3 comes first, then 2, then 1. Just remember that. We'll get to that in a second. But within population 2 and population 1 stars, basically, which are characterized by having a lot of metals. Well, over their life cycle, and these life cycles are not short, they're millions of years, maybe a billion years, these stars eventually compress, they burn out all their fuel, like they consume all of their fusible hydrogen, turn it into helium, and then the explosions occur and other processes in physics occur and actually create the heavy metals. And I think this is a plausible, there's some plausible models out there for some heavy metals being created. And so we can see areas that are rich in carbon. Most of the stars we're going to look at from the perspective of James Webb, they're almost all hydrogen, a little bit of helium, maybe a wee bit of lithium. Well, as you get into these heavier stars, you're going to get into beryllium and oxygen and carbon, nitrogen, and so forth. You're going to get into some of these heavier elements, and they need these stars to go through this life cycle of growing, compressing, dying, blowing up, and then the next cycle beginning, they blow up, become a cloud, and the next cycle begins, or they may end up as one of these 3 states, neutron stars, black holes, or white dwarfs. What if they end up back in a nebula? Then that nebula can assist, in theory, in forming more stars. So here's another one that shows the red giant turning into a supernova, kind of like that one we saw in 1054. And then that, again, could go on. If the mass is really high, it'll become a black hole. And if it's not as high, it might become a neutron star, and so forth. But the cycle can continuously repeat. I like this slide because it had a lot more details added to that basic picture, but the picture is the same. So, population 3, 2, 1 stars. Up till, I don't know, maybe the last month, at least the last 6 months, we've never seen a population 3 star. Now we think we have seen a population 3 star. What defines a population 3 star? Well, one that's just made up of hydrogen, mostly hydrogen and some helium. Doesn't have any heavy metals. Maybe trace amounts of lithium. In the corner, it compares it to our sun, which has a few of the other elements, iron and hydrogen and so forth. Let's see, I had a glass of water here a second ago. I might, there it is, right by you, Zach. I can just sneak that past you. Sorry. I'm getting over everything I had over the holidays, and so my voice is a little scratchy. I apologize for that. Anyway, we think we finally saw population 3 stars. If you look at the definitions, though, they define them. This is kind of like the transgender thing. What is a woman? Well, what is a population 1 star? It's a star that's not a population 2 star. It's almost that bad. Basically, it's got more metals than a population 2 star. What's a population 2 star? It's one that has fewer metals than a population 1 star. And that's like from NASA. I was looking at several of these websites. Anyway, but part of the evolution of stars is that, in theory, we would have moved from stars that were all helium, because that's all the Big Bang creates for us. Hydrogen. Creates a lot of hydrogen, a little bit of helium, and that's pretty much it. How do we get to all the other heavier elements? Well, we have to have this cycle of stars living and dying and exploding, living and dying and exploding, and this eventually gives us the heavier elements. So population 3 stars, in theory, should be out there, and indeed, we think we found one, which means we found a star that's mostly hydrogen. So we can tell a big story about that. Or maybe it's just a star that God made that's mostly hydrogen. I'm not sure. I don't think you can. It's kind of in a weird place in the universe. Anyway, so population 1 stars, newer stars that contain numerous heavy metals. Population 2 stars, old stars, that contain fewer heavy metals than population 1 stars. And notice how they superimpose the word older and newer here. Maybe they're older, maybe they're newer. Some of this is presumptions and assumptions, and it's woven into the text in such a way that you kind of have to pay attention to is what's the facts here and what's the story being wrapped around these facts. Anyway, but there are something to be aware of because they're getting a little more attention now that we think we should be finding population 3 stars with James Webb Space Telescope. And of course, after stars, we end up with galaxies. Stars You get 1, 2, 3, 5, 10, 15, 1,000. These stars start to cluster and form galaxies. There's there's actually 7 types of galaxies. I'm going to put 3 up here. Irregular galaxies, that's what we thought the oldest galaxies would be. Kind of makes sense. If this is all occurring through some natural process, then as the stars are kind of wobbling around out there and bumping into each other, doing whatever they're doing, you're not going to really have any form. They're just going to be interacting with each other gravitationally in other ways. And so you're going to see irregular galaxies that would be the oldest galaxies. That's what the models would predict. And then as you get into older galaxies, the old and new get a little tricky here. But as you get into galaxies that have been around a long time, in theory, then they would become more organized. So you have your spirals and spiral bar galaxies. That's about 60% of what we see. And sometimes you'll hear this word, near universe. Well, that's referring to the universe. I looked at the Milky Way, it's about 100 now. It's actually been resized, maybe 140,000 light years across. It keeps getting resized, but that's fine. Andromeda, the one we saw, the next closest one, that's 2.2 million light years away from Milky Way. Anyway, the near universe is like the first billion light years or so. And some people go out to 1 to 3 billion light years. And then the far universe, the distant universe, is the universe that's even further away than that. Anyway, when we look at the universe that we can see, our near universe mostly, because it's what our telescopes would let us get a good glimpse of, mostly spiral, that's about 60%, elliptical is about 20%, the irregular is about 20%. Well, sneak preview, guess what happens when we looked at the very edge of the cosmos that James Webb is taking us to? Yeah, it's about 60%, 20%, 20%.
You have all of it again?
Yeah,
Further out.
you have spiral galaxies at the edge of the universe, where there should not be. And at roughly the same distribution that we see them in the near universe. So this is one of the things that's puzzling, but we'll get jumping ahead a little bit. So let's look at this story, the evolution of the universe story. I threw this one in, it wasn't there last year, but it's the simplest version of it. Just to show you I'm not cherry picking this, I've got 4 of the same thing. But because it's basically the same story over and over. We start with the Big Bang. This is followed by inflation. You don't really see it on this picture. And you have this period of time where it's called the Dark Ages. Lots of things are happening in that first moment of the Big Bang, and then shortly thereafter Big Bang, like in the trillionths of a second after a Big Bang. And then the formation of elements. You've got to form all of your protons and neutrons and electrons. All that has to get formed. And then finally you leave the Dark Ages and you finally get light. And that's when you start to see around 300 million years we have light. And the first stars, these would presumably be population 3 stars, would start to form. And of course, they're going to have to live and die and explode, live and die and explode, and feed the next generation of stars. The heavier metals, the metals get a little heavier each time, over and over. And eventually, in about 1 billion years, you get your first galaxies, or early galaxies. And then finally, more complex things like solar systems and so forth. Okay, that's one version. Here's another version, doesn't have the years on it. Same idea, you start with the Big Bang, the afterglow happens, and then the recombination is followed by the Dark Ages. But you get your first stars. As we leave the Dark Ages, photon energy and other forms of energy and the basics of the atomic table are there. And now you start to, well, not the elements, but rather the subatomic elements, the protons, neutrons, and electrons. And then you end up with your first stars, first galaxies, and so forth. This is the story. So again, if we find all of this stuff that we're seeing at the end here, at the very beginning, that would be a problem with the story. Now, it's not a problem with God's creation. This isn't taking God by surprise, but it's taking man by surprise who insists on this story. By the way, you can see the Hubble telescope is peering back through time. They want to make the point, it's peering back through time. Actually, it's peering across space. And that's not the same thing. Now, we call it light years because light years is a measure of distance. But it gets into a little, we'll see if we get to that later. Okay, so here's a third one. I like this one a lot because it actually tells you you're going through the quark area, you're going through these elementary particles, antimatter, and one of the problems with the Big Bang is why we have so little antimatter and so much matter. They should be roughly balanced. They're not. Lots of problems that come out of this story, but we gloss over those, and then we have the era of nucleosynthesis, the era of nuclei, and then finally you get into the era of atoms, where we start being able to form stars and so forth. Similar, same story, a little more detail on this slide. This is a good one. Physics of the Universe website. And then finally, from the Wilkinson Microscope anisotropy, I never can say this word very well. Anisotropy probe. One of our many, we've had some great satellites. The Spitzer satellite, which is an infrared satellite, just like James Webb. But it wasn't as precise. James Webb is an infrared satellite, but it's very precise. We'll see that in a second. Anyway, the Wilkinson there, here they're showing the actual Wilkinson satellite at the end of this similar kind of drawing, and the dark ages, and the first stars here about 400 million years. And assumably, you're going to have galaxies that are going to have to form after that, because you can't have galaxies before you have stars to make up those galaxies. Okay, so that's 4 different ones. Here's the reason I wanted to put that picture up is from, this is that particular satellite's top 10. This was number 9. Detected that the amplitude of the variations in the density of the universe on big scales is slightly larger than smaller scales. That doesn't sound that profound to me, but bear with me. This, along with other results, supports inflation, the idea that the universe underwent a dramatic period of expansion, growing by more than a trillion fold in less than a trillionth of a second. Tiny fluctuations were generated during this expansion, but that eventually grew to form galaxies. So to solve some other equation problems with the Big Bang, they really need this inflation. And one of the things, and we'll get to it more in a little bit, to make inflation happen, they had to propose a new subatomic particle called the inflatron. And you can look at this. This is one of the things they've been looking for with the Hadron Collider over in Switzerland. They're trying to find these missing, they found the Higgs boson. That was predicted and found, that's good. Haven't found much since. And they haven't found this inflatron, which they need to cause inflation. Inflation can't happen without it. So they're scratching their heads on that one. Cosmic inflation began shortly after the Big Bang. This is from the World Atlas. This is not from a creationist website. Around 13.8 billion years ago, the universe burst into existence and space and time were born. The universe began to expand immediately, and within the first second of time, the universe expanded many trillions of times larger than its original size. Inflation began a mere 10 to the minus 36 seconds after the Big Bang. That's a decimal followed by 38 zeros. That's a tiny, tiny, tiny fraction of a second, and lasted until minus 32 seconds. So it lasted even less time. I mean, this is really all happening in less than a moment. And an amount of time we can't really conceive. That amount of time is unbelievably minuscule, yet it was one of the most important moments in time in cosmic history. Now, not presumed to be, not supposed to be, this is one of the most important times in cosmic history. Because they're just assuming inflation happened. A guy in 1981, 82 proposed this, and pretty soon it's part of the dogma. During that fraction of a second, the universe expanded by an estimated factor of 10 to the 27th times, one followed by 27 zeros. It would be like the Earth expanding to become the size of the observable universe in less than a second. It'd be like the Earth in less than a second becoming as big as the whole universe. Now, we just went through a little tiny light year thing. You saw how big the Milky Way is. Imagine in less than a second, the Earth becomes as big as the whole universe. Is that science? What makes that science? I mean, other than people that don't believe in God saying it, I don't know what makes that science. Now, I have a lot of respect for physicists and theoretical physicists, and I've got a little spot that I used last year. I'm going to use it again this year from a theoretical physicist I admire. But that's also some chutzpah just to say this is what happened. The exact cause of the inflation are unknown, thank you. Yet it was likely due to an immense amount of pent-up potential energy suddenly becoming released and high concentrations of dark energy, which we know today to be the cause of the universe expanding. Actually, it's one of the theories for universe expanding, dark energy, dark matter. And there's some creationists that believe dark energy, dark matter, but the jury is out on all of this stuff. Yes, sir.
I'm sorry, how does that work? Because doesn't that mean that it has to basically expand faster than the speed of light,
Oh, yeah, right.
right?
Yeah, it suspends all known laws of physics during the moment of inflation.
All right. Now I understand how they do it.
Absolutely, they admit that. All the known laws, thermodynamics, all that stuff's all suspended for this period of time, and then we turn them all back on again, and it's all fine. I am caricaturing, of course, a little bit, but it's not too bad. Here's my point. You come across a little later, this is a paper at Harvard, and maybe it didn't have it at all. And this is my point. They don't know this happened. Can cosmic inflation be ruled out? This whole paper boils down to cosmic inflation. If cosmic graviton, one of those new particles, could be detected in the future, scientists may be able to rule out the theory of cosmic inflation. So that's, to me, tells you what they're really dealing with here. And this is far from being a just so story. At least the biologists, when they tell their just so stories, they can presumably point to some field work surrounding that. This is just conjecture, because again, what you see from a star is luminosity and metallicity. The even distance is a question. Beyond the triangulated distances, we have to guess a lot of the distance. Okay, so that brings us to that. James Webb has opened up the whole world of a lot of conjecture and progress and thinking about the cosmology and cosmogony. But here we go on to the James Webb Space Telescope. Remarkable piece of science for sure. So it's mainly functions in the infrared. This is a picture before it was in space, in case you didn't notice, when it was still in the factory. I think this was like 20% of NASA's budget for over 5 years, or maybe 10 years. This was a huge project for NASA. And I'm glad they did it. It's really remarkable what's come back with. Here's the purpose. To look at the end of the dark ages. Remember those models I showed you for the formation of the universe? Well, we want to find the end of the dark ages, first light and reionization. JWST will be a powerful time machine. Again, putting time where it's really only justified saying distance. But okay, with their models, it's time as well. With infrared vision that will peer back over 13.5 billion years to see the first stars and galaxies forming out of the darkness of the early universe. The assembly of galaxies. Again, moving into the infrared is going to give us something that Hubble couldn't do. Hubble got a little into the infrared spectrum, but mostly it was in the optical spectrum of light that we can see. JWST is oriented to the infrared. The beauty of that is infrared wavelengths are much longer. I have a slide coming up on it. The point is the actual length of the wave, of the sine wave, is larger than the particles of dust that are in some of these nebula. And so they don't even show up. We can look right past them. They don't even interfere with the infrared signature that we get from what's behind it. So we're looking right through clouds. That's pretty cool, and that's what the infrared spectrum buys us in these satellites. We see it, and of course they're going to expect to see the birth of stars and protoplanetary systems, and the origins of life. And by the way, if I do another talk this year, I think it has got to be on the origins of life, because they're all tying this into, oh, we found this particular chemical, or we found this particular molecule, and this must mean life could be present on it, or we found water, or life could be evolving on this planet, or on this exoplanet. Boy, nothing could be further from the truth. If there's anything that's further out of reach than ever before, it's the original life stuff. It's amazing what's going on in that field. I think it's even more amazing than what's going on with Big Bang cosmology, but that would be another talk. These are the 4 big goals of the James Webb Space Telescope. Here it is, kind of compared. It looks roughly the same size, but what's not the same size is the mirror. The mirror is much larger than it is on the Hubble, and that's because it's kind of remarkable. And there you can see the Hubble primary mirror versus the James Webb. I think it's, 9 point something meters, around 21 feet or something. The James Webb mirrors. And it's these sectional mirrors. They are gold. If it looks like gold, that is gold. This is not a cheap telescope, by the way. But it has remarkable properties, as we've known gold has had for a long time. And so it's entirely different. And we'll get to a few more things as to why. And in terms of size, it sits on top of a heat shield that's about the size of a tennis court. And it's big. And how you had to get this all had to get folded into the cone of a rocket, sent into space and then unfolded. It was actually launched Christmas Day 2021 and took 6 months to get it in place and get it unfolded. And right away it got hit with a rock. It actually has had damage already. It damaged one of those mirrors, like 3 or 5% of its mirrors got pretty severely damaged. They anticipated that. The solar system, for being so old, is remarkably dirty. Our solar system is. I think that's one of the interesting features of it being young as opposed to old. But so it got hit by a rock right away. And they actually have all these different calibrators and computer systems that adjust and change the fields of vision and rule out that little space of broken mirror and create everything else the same. So there's redundancy in those mirrors and the way they image everything that let them, that was anticipated and they totally recovered from. And in fact, the good news is they use far less energy putting it into space This is a one and done, like Spitzer and like, or I think it was Spitzer. Several of these are one and done space telescopes. Hubble could last a long time because we can get to it. We can refuel it. We can repair it. We can't get to this thing. It's close to 1 million miles away. We'll see that in a second. And we can't refuel it. So once its fuel's gone, it's done. They left a port though, in case we figure out how to do it. And I think it's maybe 10 or 20 years life, but it's because we use so little energy getting it where it needs to be. It actually is going to get some extra years of life out of it, which is cool. Different views of it. What's remarkable about this telescope, the top side is cold because infrared is heat. We detect infrared energy as heat, and that's what the James Webb Telescope is detecting. If it were sitting on the planet Earth, I think I used this last year, and somebody asked me about it, it's so sensitive to heat, it could detect the heat of a single bumblebee on the surface of the moon. You know, if we were just two bodies floating in space and we were sitting here with no atmosphere, that James Webb Telescope sitting on this planet could detect a single bumblebee of heat on the surface of the moon. That's how sensitive. It's sensitive down to a single photon. This thing is really remarkable. And so one of the things that makes that remarkable is keeping it so cold. They keep it under 50 degrees Kelvin, or under 223 degrees centigrade, 369.7 Fahrenheit. The heat has to be kept away from the actual telescope side. And on the back side, it's really hot. That's where the sun feeds it energy, and that's why they have to keep it. So on the hot side is 185 degrees. That's about boiling water temperatures. On the cold side, minus 388. There's also a chiller. One of those instruments inside that little red box there has a chiller that takes it down to like 6 degrees Kelvin. Just a hair above absolute zero. It's not cold enough on the cold side. They actually had to build a chiller into this thing, and they've got some remarkable technology doing that. Anyway, so how do you, this is a good insulator. Well, if you had a blanket this good, you'd only need one to get through the whole winter, right? Because something's that hot on that side and that cold on the other side. This is some pretty remarkable technology. It was all folded up into a cone. It's actually 5 layers of this really interesting material. The shiny silver material of the 5-layer sun shield is a complex and innovative feat of material science and engineering. Each layer is made from a unique composite material. Each has a specific thickness and size, and they must be precisely separated in the distance between them in space. There are even spatial seams and reinforcements to limit meteorite damage. The layers work together to reduce the temperature between the hot and cold sides by approximately 570 degrees Fahrenheit. Each successive layer of the sun shield, which is captain is this material they're using, is cooler than the one below. Okay, another neat thing is the orbit. So I like this picture because you see the Earth and the moon. That little thing right around the Earth is the moon. The moon's about 250,000 miles away. I think I put some numbers up here. Yeah, 239,000. James Webb is about 1 million miles, 900,000 and change out there. And it's in what's called Lagrange point 2. These Lagrange points, one of the reasons Newton said what he said about our solar system, when you start, there's a 3 orbital body problem in calculus and physics that is just almost unsolvable. We have real trouble trying to model 3 gravitational bodies in orbit and working with each other. Anyway, so the moon, the Earth, and the sun, that's a very difficult thing to model. And I don't even know that we've achieved it yet, but we keep getting better with our computers and so forth. Anyway, these Lagrange points was a guy who figured out way back yonder that if you have, a strong body and a weaker body, and you use some of Newton's calculations, that somewhere between these 2 bodies, there's roughly a point where you've got equilibrium in terms of the gravitational pull on that object between that body and this body. And if this is a big body and that's a little body, well, then it's probably going to be a little closer to the little body, right? Because he doesn't have as much gravity to attract with. Well, anyway, this is the start of the thinking on these Lagrange points, and 2 of them sit off at 90 degrees. One is at the opposite end, that L3, but the L2 point is a place in space past the Earth where we can keep, with minimal energy expended, a certain thing sitting out there, relatively low energy, just sits out there. And that's important because we don't have an unlimited supply of fuel. So roughly the L2 is 932,000 miles from Earth. This is called a halo orbit. See how the moon goes around the Earth? And although that we see full moon, half moon, we see solar eclipses, we see lunar eclipses. There's shadows cast by the moon, there's shadows cast by things when the moon gets between the Earth and the sun and so forth. Well, that sensitivity of that telescope is so much, it can't have any shadows. So the Earth's shadow cannot touch it, the moon's shadow can never touch it. And so it sits in this halo orbit, which is outside of this. So imagine the Earth and the moon are that way. Now you've got this halo orbit out here, which is like a perpendicular orbit. So that the actual telescope never gets in the shadow of the Earth or the moon, regardless of the stage of the moon. And that's going all the way around the sun this way, right, over a year's time. So pretty neat science, pretty neat technology. And that's how sensitive it had to be able to do what it does. And that's what all this is going to say at that point. It resulting in stable temperatures for the structure of the dark side is critical to maintaining precise alignment of the primary mirror segments. Okay. Little quick drink. Is this making any sense? I hope. Okay. Good. I'll answer questions later. And for the best question, I have a free calendar. But I get to decide whether it's a good question. Mark didn't know that when I bought 2 calendars. One was to give away. The electromagnetic spectrum. This is just showing you the difference between the visible wavelengths. And that's, we see the colors. If you ever get a prism, you probably did this in school, where you get a prism, you break down white light, and it separates out into the various colors. And this is similar to what's happening with these telescopes that are optimized to detect light or light energy in a certain perspective, in a certain spectrum. And the spectrum of the James Webb is oriented to the infrared, the longer wavelengths. Now, it isn't that there isn't some overlap. There is actually some optical overlap into the optical with James Webb, and there's some overlap into the infrared with the Hubble. But again, Spitzer was totally infrared, and James Webb is basically infrared. So here's the difference. When you're peering into space, there's a lot of dust in space. There's a lot of stuff to peer past. Well, when they looked at Hubble, here's Chandra Deep Field. That was another telescope project. JWST, they believe it's peering all the way back to 0.3, which is about 300 million years after the Big Bang, using their times. I thought I had one here at the Hubble. But yeah, Hubble can see about 600,000 years after the Big Bang, and the James Webb, 600 million rather, James Webb can see to about 250 million years after the Big Bang. So what do you expect to see? Well, this picture kind of shows what we should expect to see. A bunch of not well-formed stuff, a bunch of cloudy gas, maybe just the earliest beginning forming of stuff, and certainly not these things at the end, which are our spiral and our elliptical galaxies and our bar spiral galaxies. No, none of that. We're going to see just the kind of the dusty mess that it all began with. That's the story that we're trying to fulfill our expectations with this particular telescope. Okay, well, let's just look at before I talk about some of the findings, let's look at some of the really neat stuff. This is the Hubble image of the Carina Nebula, and this is the James Webb image. And so one thing you'll notice is there's a lot of dust and cloud, and so the James Webb is peering past that and giving us a lot more resolution, a lot more starlight, a lot more visible separate stars and galaxies in that field of vision, things that weren't visible with Hubble. This is similar to another one, comparing different the telescopes to each other. You can just see a lot more detail coming out of the James Webb. And I probably won't do it. I have a paper on my computer. It's like 10, 15 pages long. You'd be amazed how much information is in a picture like that. The science behind, and they're analyzing the spectrographic imaging of all of these different lights and the different angles of light and the gravitational forces and the math that goes into all of this stuff, explaining rotational movements and interactions between the bodies. It gets really interesting and complex and way beyond my ability to actually follow, but I do appreciate that these are smart people working on this stuff. There's another one that's Pillars of Creation. The Hubble kind of gets you right through some of that cloud into some of the more detail with the James Webb. This is a famous one, the SMACS 0723. I'll bring that one up again. This is a famous picture. I wish my little thing was working. I would show you, but it's just not. I can do it with my mouse. You'll see this picture a lot. Just people want to show you about you see these? I call this the ... and then they got these two down here. Like boink. That's not a scientific description, but when you see that pattern, you can see it over here in the Hubble version. See those four straight lines? I don't know if they're galaxies or just stars. And then you see the pair down there. You'll see this SMACS 0723 image occur quite a bit. And just what we got from that alone is remarkable. I think the paper I have is just on the SMACS 0723 image. And what we're also able to do is download Hubble data, which is primarily in the optical spectrum, JWST data, primarily in the infrared, and combine them and get an even richer view of that section of space and what we're looking at. So the science is excellent here. The engineering is phenomenal. This is remarkable stuff. And so what are we finding? Well, one thing we hope to find was an answer for the Hubble constant, or what's called the Hubble tension. Hubble constant is a number that measures the expansion rate of the universe. And it's complicated. It has to do, it's not very terribly complicated. It's like megaparsecs over something, I forget the exact formula. It's just this little equation. It's a little more than E equal MC squared, but it's not that tough. Anyway, just forget it offhand. But it involves parsecs. By the way, if you ever hear the word parsec, that's basically 3.26 light years. There's a reason for it. We won't go into that. But a parsec is just another way of measuring space, or a distance, rather. It's about 3.26 light years. So you see the word parsec once in a while. Anyway, so we had all these different beautiful satellites we're putting up, and all these different methods, the Cepheid star, the standard candles. They're giving us different numbers for this Hubble constant. If you recall, I think this was the analogy I used last year. Imagine we have a train. It's a mile-long train. Half of it's in Missouri, half of it's in Kansas. It's driving across. And it's the same train. We all know it's the same train. We set up instruments to measure its speed in Missouri. We set up instruments, billion-dollar instruments, to measure its speed in Kansas, and it comes out with a different speed. The speed does not match. That's the problem with this Hubble constant. We don't get the same number from these. We get basically two sets of numbers. There's clustering at a high and a low value. And basically, JWST came in and said the Hubble number is the right number. Well, that's no good because that's just a number in the other cluster. We wanted something to unify the clusters and give us a true answer. JWST didn't do that for us. The Planck Space Telescope, we get all these different numbers, and there's a lot of science behind why we get those numbers. I thought I would, well, the Hubble shoes measurement, I mean, they knew about this problem, and so Hubble was supposed to solve it, and it just made it worse. This is what the Hubble Space Telescope was built to do, using the best techniques we know to do it. That's from NASA. And so they predicted a lower value for the Hubble constant, 67.5 or so. They got a 73. And again, that may not seem like a lot. It's just a number, it's two different numbers. Why would we care? Well, imagine your speedometer. Are you going 67 or are you going 73? It matters. It matters, especially if you're talking about space and how things are working out there. It's kind of confusing. So, oh yeah, this is Sabine Haas. She's one of these popular physicists I listen to, and I think I used her last year too. I'm going to play a little bit of her stuff. She's funny, but she's actually very bright. A little bit of an East German accent.
New data from the Webb telescope confirms that something is wrong with our understanding of the universe. For the past 5 years or so, cosmologists have been worrying about a discrepancy in their data known as the Hubble tension. The Hubble rate measures the current expansion of the universe. The issue is that different measurements of the Hubble rate give different results. If our model for the expansion of the universe was correct, this shouldn't happen. A letter that was recently published in the Astrophysical Journal looked at some of the data which contribute to the Hubble tension. These are data of a class of extragalactic variable stars that were previously observed with the Hubble telescope. The same stars were now also observed with the Webb telescope, but at a better resolution. The data from the Webb telescope agrees with that from Hubble, which rules out the possibility that there was an issue with the Hubble data. So it confirms the Hubble tension. I found it interesting how the opinion about the Hubble tension has slowly changed in the community. Initially, a lot of astrophysicists thought that it's an issue with one or the other experiment or data analysis. However, most of those issues have now been checked, and the evidence has become increasingly solid that it's really a problem with the model, not with the experiment. What do you think, Albert? Is this going to shake things up?
She's got a good sense of humor.
New data.
Okay, moving on. JADES, so this was one of their acronyms. James Webb Space Telescope has the Advanced Deep Extragalactic Survey, called JADES. JADES for the James. It basically is the next generation version of the Hubble Deep Field. And I'm only putting it up here because this, if you look at this on all, because it's just quite, sorry, I'm not holding this very close, sorry. If you look at this as all, you're going to come across some of these acronyms. JADES is another one you'll come across. And what is it talking about? Well, it's just an aspect of what James Webb is designed to do. And of the findings, this is the top astronomical findings of 2023. So this is new material. This wasn't here last year. This is the findings. As an astronomy conference that opened this year, astronomers announced a surprising find in the James Webb Telescope data. That was in early 2023. The early universe seemed to host more and bigger galaxies than astronomers had expected. By the way, each of these underlying things is a link. If you go to the skyandtelescope.org website, each of these is a link to more articles than astronomers had expected, calling into question either our understanding of galaxy formation, or of dust formation, or of cosmology itself. These are fundamental things that we are seeing. While some initially doubted the extreme distances of the galaxies involved, remember when Mary Schweitzer came up with soft tissue and they said, oh, it's bacterial biofilm. It's not soft tissue. No, it can't be soft tissue. It was soft tissue. They got the same reaction with these early galaxies. I saw one astrophysicist said, those aren't galaxies. They're really, really, really big stars. Just one star. It's not a galaxy yet. But, then he's got a problem. How do stars get that big and they're full of metal too? But anyway, the results published later in the summer backed them up. And then that's referring to this paper. I did click on that link. The cosmos in its infancy, JADES galaxy candidates. That's why I gave you the word JADES. Z greater than 8. Z is a measure of redshift. Anything greater than 8 is getting pretty old. We have 9, 10, 11 out there. I'll show you a really remarkable one coming up soon. And basically, we present a catalog of 717 candidate galaxies, greater than 8, when the universe was just 600 million years old. Remember, we're not supposed to have any galaxies until 1 billion. That was what those pictures were showing. They're going to upgrade those pictures very soon. That's why I wanted to grab them. And but now we're seeing 717. And by the way, that's just looking in one little section of space. I mean, the Webb hasn't been all around the sun yet. We haven't done a full 360 of our whole field of vision from this point in space. That's just since they've launched it. It's only been out there a year. And I guess technically it has been out there a year, and it started filling in July. So I take that back. It's been out there for a year and 6 months. It's gone around the sun at least once. But this is not based on a full survey. But this is based on, in fact, it's based on SMACS, I believe. Now, we'll get to that. I don't want to jump ahead of myself. So what are they seeing? They're seeing young but mature galaxies, spirals, bar spirals, ellipticals, and some irregulars. Again, roughly in the same proportion we find them in the near universe. So what are some of these galaxies? I had this one last year because I think it's a pretty good one. And that's actually, this was found by Hubble. We just got more clarity on it from James Webb. Z11 is thought to have originated around 400 to 420 million years after the Big Bang. It's thought to be about 32 billion light years from Earth. Now that's something that gets interesting is because the universe is expanding, you take a star that's 13 billion years old, how far away could it be? 13 billion light years? No. It could be 32 billion light years because, again, expansion is happening and it changes all the numbers that get kind of crazy. Milky Way's estimated, and this estimate was about 170,000 light years. Again, it has gone through a few re-estimations. 11.9 Z factor. By the way, that's if you just took any of these. I think that earlier video I put in showing the light year, the light 100 years, and then showing us the Milky Way, just the Milky Way, one galaxy, our local galaxy. You get a sense of these distances. The car at 120 miles an hour, these numbers are extraordinary. Any of these things. By the way, the new telescope they're proposing now, they would have to figure out a way to go 4 times faster in space travel than we can currently go. Voyager is going about 1 million miles a day, and they need to go 4 times that fast to get this new telescope out where it needs to be in 25 years. But I'll get to that in a second. That's just curiosity for the next big telescope. It's going to tell us even more about God's wonderful creation. And so what else is unfathomable? For as high as the heavens are above the earth, so great is his steadfast love toward those who fear him. And as far as the east is from the west, which we know those two never meet, so far does he remove our transgressions from us. That to me, when I see the unfathomable, distances in space, I'm reminded of these kinds of passages. GN 13, is given that name because it has a Z factor of 13, and about 33 billion years, about 2,300 light years in size, so it's not huge, but it's made up of more than one star. And again, a factor of Z 13 puts it at about 300 million light years after the Big Bang. These have been, here's another view of that last Z13. It had smashed records. But wait, there's a new one. Oh, by the way, some of this is that SMACS 0723 image again. Came up in some other article I was reading. You see the straight line of dots. Again, the 4 dots and the 2 little beat points. And that tells you where you're looking at that SMACS 0723. A lot of these early findings, those early galaxies, were from that particular thing. There's papers. Did I put the name of the paper here? Yeah, Discovery and Properties of Ultra-High Redshift Galaxies. Not less than 9, but less than 12 in the JWST ERO Early Release Observations SMACS 0723 field. So the papers get labeled that way because that's what, that's just looking at that one picture. And then this paper is 20 pages long with all these doctors and smart people looking at it. Pretty neat. Okay, here's the new one. Now this one has not been spectroscopically confirmed. So this one is, the jury's still out. There's no peer review yet on this one. But I thought this was pretty fascinating. F200DB 045, I'm not sure where that number comes from, is a candidate ultra-high redshift Z greater than 9 galaxy with an estimated redshift of Z equals 20.4. Now remember we were just talking about Z11 and Z13, how remarkable and amazing that was. This says Z20.4. This doesn't even fit any of the known parameters of what we're talking about with redshift and with the Big Bang cosmology. This is another head scratcher. And yet we just discovered it, but now again, it has to be confirmed. Some of these things, the instruments, they rework the instruments and they rework the calculations and they come up with some other explanation. And it could be that this is just, it is at this point just an outlier. We shouldn't take it as much more than that. But I keep the name up there so you keep an eye out for that one coming out in the news. And it was also found in that SMACS 0723. By the way, what else are they finding? Besides all these galaxies, 700 some odd galaxies, black holes. In fact, they found this one super giant black hole. This one black hole they found is now making them rethink how black holes get formed. It used to be, you remember the stellar evolution picture I had? And you had the star, and then the main sequence star, and then the supernova, and then depending on the density of what the resulting cloud, you might end up with a neutron star, or you're super dense, you might end up with a black hole. Now they're trying to figure out how could a cloud turn into a black hole? Because they don't have time for all that stuff. They find these black holes right at the edge of the universe. They don't have time for any of that. And all of that unfolding of stellar evolution to occur, and yet they're seeing these black holes. So here's just one article. Giant black holes were supposed to be big players in the early cosmic story, but recent James Webb Space Telescope observations are finding an unexpected abundance of these beasts. Turns out black holes are at the center of most galaxies. That's kind of what the galaxies form around. There is a model being worked on. Just a few minutes left. Oh, no, I don't. But I'll mention it. There's a model being worked on. Basically, we are roughly in the center of the universe. It differs from the secular model, which says all objects are moving apart from one another. I have a balloon in my thing. I won't get it out and blow it up. But imagine on my balloon, I've got all these planets and stars and galaxies painted on the outside of the balloon. I blow up the balloon. Balloon gets bigger. Everything is moving away from everything else. So there is no concept of center. Well, the evolutionists love that. It solves some problems. But actually, if you consider that the Earth might be, not the Earth exactly, but the Milky Way roughly within 1 million light years of the center of the universe, it would also explain why we see what we see in all 360 degrees, and that way too. And also, there are these concentric circles, if you will, clustering of galaxies and of other stellar formations that occur out from us at various intervals. And I was just listening to Jason Lyle talk about this in a video last night. It's too early, like that prior galaxies too early. It may be our instruments have a bias in the way they're measuring, and they're just measuring really well at certain intervals. So we got to make sure our instruments are measuring things well. But there's actually some reasonable data accumulating that we are indeed in the center of the universe. Not exactly. Now, just like the Earth, you don't want to be in the center of the Milky Way. That'd be a very bad place to be. We'd be in a black hole, and we'd be destroyed by all the forces that are going on there. So you don't want to be right in the center of our galaxy. Just the same way, you might not want to be in the dead center of this stuff, but we are near the center, which is why we peer in all directions and see basically the same thing. We get the same cosmic microwave background signature in all directions and so forth. Anyway, giant black holes are out there too. By combining oops, sorry, I'm losing my voice again, and I'm wrapping this up, I promise. By combining data from NASA's Chandra X-ray Observatory and NASA's James Webb Space Telescope, team of researchers was able to find the telltale signatures of a growing black hole just 470 million years after the Big Bang. And again, they're using combined images from the multiple things they've got working on this problem. Okay, do we have 6 minutes left? Sure. Okay, so I want to put this Neil Turek. He's not a Christian as far as I can tell. He's a secular theoretical astrophysicist, and I used him last year, but I think it's really profound what he's got to say. So what are these people saying when they see all of this stuff? Because it's just continuing. They're continuing to find things that don't fit the current models. The Big Bang has got problems. Inflation has problems. All of these features that they've been putting in textbooks for years have real serious issues, and they're admitting it. Unlike the evolutionary biologists who will deny it to their dying breath, at least the theoretical astrophysicists are admitting it. So this is what's called the standard model of elementary particles. And I bring it up because he's going to refer to this just in passing. I want you to be aware of what he's talking about. So you've probably all heard of atoms, and atoms are made up of protons and neutrons and electrons. Atoms make up molecules. Well, atoms themselves are made up of subatomic particles, quarks and leptons, and some of these things that are mentioned here. And like we found the Higgs boson, there's other types of bosons and gluons and so forth. These things have been found. They were theoretical at first, and then they actually put together some pretty good science and pretty good experiments and found them. But they're not finding what they need to find to explain what they're seeing with James Webb, and that's what this next slide is going to be about. He holds the Higgs Chair of Theoretical Physics at the University of Edinburgh since 2020, has been Director Emeritus of the Perimeter Institute for Theoretical Physics since 2019, specializes in mathematical physics and early universe physics, including the cosmological constant, that thing, the Hubble tension, and a cyclic model for the universe. So he's had different ideas. He's written several books, and I love it. He's even a line where he says, "Yeah, don't look at that book. Go to the next book."
But you wrote along the fall a phenomenal book called Endless Universe. And in fact, that's the title of this episode. And I want to ask you, we'll get into all your incredible, delightful work, but that book is a popular book. And I want to ask you, what is the meaning of the title of the book? And what is the cover meant to evoke in the minds of readers? And we'll show a cover of this. So can we please judge your book by its cover?
Okay, well, the book was really trying to convey how exciting it is to be able to make models of the entire universe and its entire history, and then test those models against real data. And so I'm always very clear to differentiate between theorists, which I call imaginary people, and experimentalists, who I call real people.
Thank you.
And that's a little bit of a joke on complex mathematics, where you have real and imaginary numbers. But that's really the way I see things, is that the theorist's job is of course to benefit from the incredible observations which are made by people like you. Think a lot about them, try to make mathematical models which fit them, and ideally which make more predictions, which then people like you can check. I want to emphasize that most of what theorists do is wrong. And one of the main, sort of, in my view, most important things about a theorist is they should be willing to recognize when they've gone wrong. Put themselves up to scrutiny to test both mathematical and observational, and if either fail, move on to a better theory. So although that book, I was very excited at the time, we had a theory which was connecting the Big Bang with string theory, and a development of string theory called M theory. I was excited about it at the time, but I have to say, the more I thought about it, the more I doubted its foundations. And so, although I was excited about Endless Universe, I've written another book since called The Universe Within, that is actually also a popular book, which again tries to give a picture of what it's like to think about the universe. But what I'm really excited about now is almost the opposite of what's in the Endless Universe, which is that the main point is that observations of the universe made by people like you have revealed something incredible, which is that the universe is unbelievably simple. And by simple, I mean very economical in what it takes to describe it. You just need 5 numbers. And so far, there's no evidence for anything more than those 5 numbers. Whereas, when we look at our theories, they have become unbelievably complex, arcane, with a million assumptions and fixes. And starting about 5 years ago, I basically decided, this has all become a bit of a joke, to be honest. What we should be doing is being strongly guided by the data to constructing much simpler models of the universe. And by simpler, I don't mean less precise or vaguer or anything like that. I mean that basically the evidence is we've been missing something. And I'll go into detail about what that something is. And once I made this switch, as I said about 5 years ago, I said, look, I'm just not willing to build these arcane models anymore. I'm going to be ruthlessly self-critical, meaning that I'm not willing to introduce even one extra field into the standard model. Standard model is basically a well-verified picture of what we know about physics. I'm going to be extremely reluctant even to introduce one new ingredient. By that assumption, I'm just ruling out all the models that have been developed in the last 40 years. Everybody's been introducing extra fields, extra particles, extra dimensions. What do we end up with? We end up with the multiverse, which is the least predictive theory ever. Okay. And
I was predicted.
well, it predicts the most, but it's the least testable, let's say. Whereas the evidence, both on the very large scale and on the very small scale, has gone in the opposite direction. So the Large Hadron Collider, the greatest experiment ever built, discovered the Higgs boson and absolutely nothing else. Okay. So most theorists, like me, 99% of theorists, are extremely disappointed at that result. Oh my God, everything we've done for the last 40 years has led to nothing. There's just no extra particle to be found. And I'm exactly the opposite. What my interpretation is that nature has been smarter than we have been. And nature figured out how to get away with just having the bare minimum. The Higgs boson, which is necessary to make standard physics work, and no more. So on the tiniest scale, we have this surprising economy in the laws of physics. On the larger scale, it's the same thing. The Planck satellite, subsequent experiments, your forthcoming very exciting experiment with the Science Observatory. So far, these have revealed nothing new. That's not bad. That's a huge challenge for fundamental physics. It says to us, maybe we're working on questionable set of assumptions.
So, many things could follow here, but I think the gist is that they are without excuse. It's like Newton said. Newton explained it. You need God to explain what we're seeing, even in the solar system, let alone the rest of the universe. And so I think they're getting so close, but there's still no room for God in their solutions. Anyway, we had a whole presentation on that, so and I'm out of time. So I'm going to defer, and we had a great presentation, covered most of these. So go back and see that one. If we got it on the web somewhere, maybe on our.
It'll be on YouTube, yep.
It'll be on YouTube, there we go. And there's also creation.com, nice summary of that, because everybody asks about this. If the stars are so far away, how can we only be 6,000-year-old planet? There's ways. God is amazing. And so I conclude with great is the Lord and most worthy of praise. His greatness no one can fathom. One generation commends your works to another. They tell of your mighty acts. They speak of the glorious splendor of your majesty. And I will meditate on your wonderful works. They tell of the power of your awesome works, and I will proclaim your great deeds. The end. Thank you.
I've never really needed a microphone. You know, you've heard of foghorn leghorn?
Yes, sir.
Yeah, that's me. Before we get to questions for Steve, first of all, I forgot to thank Pastor Dave for giving us our meeting place here. Thank you, Pastor Dave. And we'll be here the next 2 months. And next month, our presentation will be by Dr. Joel Brown. And it is Church Fathers in Creation, the Good, the Bad, and the Ugly. So I don't know how you know what they look like. But it should be an interesting presentation about what the beliefs were way back in the beginning and how I hate to use the word evolved, but how things evolved over the years to where we are now. And we're looking forward to that. Remind you, we have a book table over there, and we have fossils, free fossils, if you'd like one, with a description of what it is. And we have the tracts that we have for sale over there, as well as the books. And everybody take one of the tracts, so you can order them online if you like them. I had one other thing, but I forgot. So first question is this. Turek said, we're expecting all this complicated stuff, and it's really simple.
What he's contrasting is the simplicity of the way things are put together. I think it was either Gary or Scott last year that the word efficiency comes to mind. What we have is a remarkably efficient working system, and they're trying to find a natural creation for that system and stumbling horribly at it. And smart people for decades have been working on this, and they can't find a way to get this resulting system through any means, even when they reach down into the extreme theoretical. But what they do know they have, and they can test and experiment and see, is this beautiful, remarkable, efficient system.
Right, and in that video that Scott and I did, we talk about, and this track, thank you, is we talk about systems, because any system requires intelligence. It can't be a system without that. And, you know, you talk about something like the highway system.
That doesn't have intelligence.
Well, it does to this extent, thank you. It does to this extent. I mean, the idea was to connect our major cities. They didn't just randomly dump asphalt and concrete. Somebody had to design it. The idea was to connect the major cities, right? Using materials that would withstand all kinds of weather and heavy loads being carried. And so the system was designed. We also have a political system. There's nothing wrong with the system. The problem's with the people that are implementing it. But at any rate, any system requires intelligence. And that's so much of what science tries to diffuse, I guess you'd say. Even in biology, we have 13 systems in our body. We have circulatory system and a respiratory system and a reproductive system, and we have all these systems in our body, and they all work together, but they try to tell us there's no designer. There has to be a designer. So when he talks about it being simple, one of the reasons it's so complex now is they started with, okay, there's no creator. How do we get there? And they built this big monstrosity because they had to make it fit kind of what they were observing. And now the more and more they observe, the bigger the monstrosity gets, correct?
I think that's what he's alluding to, yeah.
So, questions for Steve?
Yes,
You guys would.
Yes, sir.
Why do stars need hydrogen?
Why do they need hydrogen? Well, hydrogen apparently is the most abundant element in the universe. Why do they need it? You know, I'm not really sure why they need it. It's just that even our sun is 97% hydrogen. So when we look at these stars and we talk about, oh, this has a high metallicity, we're only talking about that wee little bit that's left. That one picture I had showed 3% is where you see the iron and the carbon and all those other elements, and the helium and so forth. So hydrogen is consumed through fusion and converted to helium at the core of the star. But beyond that, the physics, I'd be messing up to try to explain the physics of how that fusion process works. But that apparently hydrogen is the fuel of stars. And as they get old and burn up all of their hydrogen, because I did read through one explanation of a life cycle of a single star, and it basically converted at its core, everything became helium, and then some other stuff went on that ends up either making it explode or implode. But yeah, I guess because it's fuel is the short answer.
Yeah.
Yes, sir.
So I'm intrigued by the population, star populations and their distribution. And we didn't get much into that. You alluded to the fact that they may have population for each star. So I suppose in the secular worldview, you would expect to see some sort of distribution, change in the distribution of those star populations as you go through a deeper look back time.
Right.
With P3 and younger, and then transition to P2, or the other way, P1, P2, P3. Is there a distribution?
None that I saw. And then I was actually looking for something to put on my chart to differentiate P1s from P2s. And they were just a little more, few more metals, fewer metals, more metals, fewer metals. Our sun is a P1 star. But I didn't see anything referring to distribution or, now they do, so let's see, is it P2? One of those does occur at the core of galaxies and in the gas surrounding galaxies. That they did find a higher incident of one of the types in those two spaces. I didn't try to read the explanation as to why they would end up there and there. But in between, you have the other population. Yeah, I'm sure there's a story to it.
But as far as like a look back time, they don't.
I didn't see anything like that. In fact, the one they found, I don't even think it was that crazy of a redshift value. And I believe they found it. There's a YouTube video on it. It's very interesting. It's pretty. It's really pretty blue, just ball. And they said this might be the first P3 star, because if you read even older, 5-10-year-old, we've never seen one, but we're hoping to find one. And there's this YouTube video out there now that says we may have found the first one, and it's really pretty, but apparently it's just sitting out there, and no progression type of thing. Context.
But with the age of with their supposed age of the universe, we shouldn't even see any P1 stars, right?
Right. We should only see P3 stars in early stages of formation at the edge of the universe, right after the Big Bang. And then as you move forward in time, we should see them progressing to P2s and then progressing into P1s, P1s and P2s forming the galaxies. And as the galaxies have life cycles of their own, begin to structure themselves around the black hole, something had to become that center of point of gravity, and then the spirals start and all that kind of stuff. But yeah, that all takes time in the evolutionary story. And that's not what they're saying.
It seems to me that this could be a really interesting way to compare the competing models, because in the creation model, we wouldn't expect, at least naively, to have a change in the distribution of those star types.
Fair enough. Jason Lyle did some predictive modeling before the James Webb JWST results were published on what they would find. And I haven't read what he put out because he was on a panel and they said, nobody predicted this. And he raised his hand and said, I did. And so I need to read what he actually said. But he said he did put out a paper that described from a creationist perspective what we would expect to find from James Webb as opposed to what the secular people expected to find. Other questions? Yes, sir.
I don't understand, when you talk about time and distance, the difference, in layman's terms, what you're talking about. You're looking back at those models.
You're
Almost said
looking-
looking back to the Big Bang, but when the telescope's out there, it's just looking in distance, right?
Right, you're just looking at distance.
So
What
there
they
is no
see-
time that we're looking back at?
Technically, there's not, because they're superimposing the time concept on it by using the term light year. And we know that light travels, what, 186,000 miles per second, and then, how many trillions of miles per year, and so forth, and quadrillions. But it's a measurement of distance. And it's very easy to have your mind slip into, okay, if the light left, like we do with the sun, so it takes about 8 point something minutes for light leaving the sun to reach the earth, based on at least one theory of the speed of light, that theory being that it's constant and not Jason Lyle's theory that it's not necessarily constant. Based on that theory, that we can take time and tie it into the concept of distance. But when we look back into the cosmos, all the theories start to get stretched. And that's kind of my point with the Hubble tension and with these other things that the explanations are not there for what we're seeing in a lot of these ways. Even the way the physics, the Hubble tension is nice because that's just taking great instruments, looking at the same phenomena and getting completely different results. So so I'm only saying you should be cautious by equating the concept of time with the concept of distance.
Which is it when they're looking
It's
out?
distance. These Z factors are distances, and it's based on the redshift of the wavelength over that distance and the expansion rate. Because because the universe is expanding, the light is stretching. And so as you get further away, you've got more stretching that has occurred. But there's a lot of good physics on this stuff.
And the Bible says 16 times that God stretches out the universe.
Right. By the way, I know we're over. The next telescope, you should at least hear this. So one of the things that you've probably heard of the privileged planet, where we have this great position to observe all this neat stuff, eclipse and then our position between the arms of spiral galaxies and so on. Well, it turns out one of the things that's really helping us with James Webb is a particular galaxy cluster that is allowing us to do gravitational lensing. What gravitational lensing is we have this large galaxy cluster that bends light as it passes by, and it creates a lens for us so we can see much further with more accuracy and higher resolution deeper into space than we could otherwise see. So the idea for the next telescope is to put it out and where they think Hubble cloud would be, which is fictitious, but to put it out basically, what is it, 29 light days out, far further than Voyager is. Voyager is about it's in the roughly in the that domain around the solar system. Forget the name of it offhand. Anyway, it would have to, just to get there in 25 years, this is the plan, this thing would have to travel 4 times faster than Voyager. So they're going to they have 2 different maneuvers. They have a sun sail. They have sound theoretical basis for making things run faster in space. And so this sun sail, basically, if they open it at the right time, as they're orbiting the sun, it'll create a slingshot effect. And then they combine this with this other maneuver, and it's got this guy's name on it. I forget the name, Earth maneuver or something. Anyway, that will give them this really intense, 4 or 5, 6 times the speed of Voyager. We're talking over 100,000 miles per hour. It's sailing. And but one of the problems is anything you sail out in space that fast, how do you stop it? You can't. Well, the beauty of the gravitational lensing concept is that you don't have a focal point. You have a focal channel. So once they get to the right spot, they'll get the effect of gravitational or lensing around our sun. So it's called SGL, solar gravitational lensing. Keep your eye out for that particular acronym. And it'll be after I'm dead, because they won't even get it in place at the best, they haven't got it in space yet. I mean, it'll take 25 years to get to where it needs to be. But once it's there, it can keep traveling fast, because basically within that tunnel, it remains in focus. As far away as, and it only gets better. It's really strange. Physics is really strange with gravitational lensing, but it'll stay in that, zooming out further and further and further, and give us these great images of whatever, I guess, is on the opposite side of the sun. It's some neat physics, and it'll be even better than James Webb, but it'll have to be, one of the kids here will have to do that talk for you someday.
Man, oh man, I always say that that's my age, that my brain is full, so if I learn something new, something has to fall out. I hope I remember my wife's name when I get home. I got so much new stuff. One more question.
So with that, so taking a picture with that telescope, how long would it take to get back to Earth?
A long time. Yes. So they right now with some of these distant galaxies, they get like single pixel resolutions. The resolutions are horrible, but with this SGL telescope, they would get megapixel. Well, it was for exoplanets. They would get megapixel resolution of this one particular exoplanet they're looking at. Sorry, I need to talk more about exoplanets and why they're not a fantasy for evolution either, or for life originating elsewhere in the universe. But maybe for another talk. But anyway, it was to get megapixel resolution on one of the exoplanets we're looking at now with a single pixel resolution, which is horrible. We get this little dot. And, what does that mean? I study it, but anyway, the time, because you are out that far, yes, it would take 29 days at the speed of light, right? You're at least that far out to send any signal back to Earth for us to then interpret.
All right, so if there are any more, well, first you got a calendar to go.
Yeah, so who had the best question? That was a good question, Tatum. Any other candidates for the best question?
Well, we had Joel and I forgot Joel.
Andrew.
Joel's out, he said.
Yeah, Joel's a ringer. He's good, so. Well, you want a calendar?
Yeah.
There we go, thank you.
All right, so you can keep that, okay. Thank you everyone for coming, and we can mingle for a while. David, there's some snacks over here if you want to ask Dave or Steve some questions. And we also, Hannah, raise your hand. Hannah Klein is back there, and she gave a talk 2 months ago, right? Last month, 2 months ago in November on distant starlight. So if you have some questions about that, Hannah will be around for a little bit. And everybody enjoy some fellowship, and thank you for coming. We'll see you here February 12th.